Alright, chapter 7, starting off here with polynomial functions. Objective, rigorous thinkers and learners will be able to evaluate polynomial functions and identify general shapes of graphs of polynomial functions. So we should get a pretty good idea of what these graphs are going to look like by knowing something about different functions. So some terms here that we should recall. A polynomial is a monomial or some multiple monomials. Therefore, a polynomial in one variable is a polynomial with only one variable, like this, 3y squared minus 3y plus 4. So you have a polynomial that just has one variable in it. Maybe different terms or different degrees, but that's okay. And the degree of a term, this is the sum of the exponents of variables of each term. So sometimes we might get something like this, right? Xy squared. Well, that's a 1 degree, that's a 2 degree, so the degree of this term is 3 because it's 1 plus 2. Degree of a polynomial, this is the highest degree of a polynomial's term. So for example, up here, the highest degree is this one, so the degree of this polynomial is 2 because that's the highest one. So here, we're going to find the degree and leading coefficient of each polynomial in one variable. It is not a polynomial in one variable. If it's not a polynomial in one variable, explain why. Okay, first thing. Well, the degree in this one would be 4, and the leading coefficient would be -6. Okay, that's what that one would be. How about this one? Well, this is not a polynomial one variable because it has x's and y's. But we can still find the degree and the leading coefficient. Let's check it out. So degree is going to be the one with the highest degrees. Well, this one has 1, this one has 7, this one has 11. So the degree is 11 and the leading coefficient is 9. Okay. Standard form, this is when it goes in descending order. So we start with the highest degree, go down to the lowest degree. So let's take a look here. We're going to find the highest degree term. And I'm going to kind of, because there's so many terms here, I'm going to kind of cross them off as I rewrite them. But we're going to write it in standard form. So the highest degree is this guy. So we're going to write that one. 6x to the 7th, cross it off. What's the next highest degree? I see the 5th. So I'm going to go plus 3x to the 5th. The next one's going to be minus 2x to the 4th. The next one is going to be plus 4x cubed. Fix my x there. Next one's 5x squared. And the next one is just plus x. And there, we've written that thing in standard form. So, why don't you go ahead and write this guy in standard form, starting with the highest degree first. You could pause the video because I'm going to put the answer up in just a second. Okay, here's what you should have had. 7x to the 5th minus 5x 4th plus 2x cubed plus 4x squared minus 3. Just write them all in descending order. Not super hard. Okay, so now let's get into the meat of this. It says, show that the polynomial function f here, basically, f of r, gives the total number of hexagons in a honeycomb when r, or rings, is 1, 2, or 3. So as we plug in r, it should give us the total number of honeycombs. Well, look. For one ring, look, we just have one hexagon. For two rings, we have 6, plus this one is 7. For 3, we have, count all these ones up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus this 7 in here is 19. So we should get, if we want to write this in here, 1, then 7, and then 19. So what you're going to do is you're going to plug in 1 for this guy, plug in 2 for this guy, plug in 3 for this guy, and see if you get back 1, 7, 19. This equation here should kick back these numbers. So I'm going to let you guys go ahead and do that, see what you find out, and then you can check and see if you did it right. Okay, as I worked out each one of these, f of 1 gave me 1, f of 2 gave me 7, and f of 3 gave me 19, which is in fact the pattern that we saw by just counting. So the next part of this is find the total number of hexagons in a honeycomb with 12 rings. So if you were to plug in 12 for your number of rings, how many hexagons would you have? Go ahead and work that one out on your own, and I will do it. I'll put the answer up in just a second. Okay, so this one took a little bit more work probably to figure it out, but not too bad. Just plug in a 12. When you do that, you should work it out, and finally you should get 397. That means at the 12th ring of this guy, you're going to have a total of 397 hexagons. All right, let's go to the next page. All right. Now, what if they ask you to plug in a variable into a function? Well, let's see what that would look like. See here, they're asking us to find p of a squared. So that means we need to be able to plug a squared in for x. So p of a squared would just be a squared, in parentheses, cubed, plus 4, a squared squared, minus 5, a squared. Work this out, you got an exponent to an exponent, so that means you multiply, so you get a to the 6 plus 4a to the 4th minus 5 a squared. And there you have it. That's all they want you to do. Be able to plug one expression into a function. So let's try that again over here. I want you guys to give it a shot. It's a little bit trickier here. So what are they asking for? They're asking for qa plus 1 minus 2 times qa. So I'm going to help you set this up. Q of a plus 1 we're going to do over here on the left. In fact, I'll do it in blue. And then I'll do this in red. So Q of a plus 1 is going to look like this. A plus 1 squared plus 3 times a plus 1. That's a plus 4. Okay, but now remember we're going to do minus 2 times q of a, which means we're just plugging an a into this function now. So that's just going to be a squared plus 3a plus 4. And now we just have this long algebraic problem to work out. The only thing that I see students get hung up on is this thing right here. This is not just a squared plus 1 squared. That's not what this is. This is a binomial times a binomial. So you're going to have to do a box or something. So remember the box, if you want to do a plus 1 times a plus 1. It's just like FOIL, but I like the box because it keeps things a little bit more organized. So this whole first expression here, just this part, is a squared plus 2a plus 1. Okay, I'm going to let you guys work the rest out so you can kind of test some of your algebra skills here. But you should be able to simplify this down to one polynomial. So go ahead and do that. I'll put the answers up in just a second. Okay, another thing that I've seen students make a mistake with is that this negative 2 out here needs to be distributed to every term. So all of these terms become negative. So then as you simplify, you should go down to negative a squared minus a. Okay, now let's talk about when we actually graph these functions, okay? If we have a degree of 0, that's just like, y equals 5. Degree of 0, we get a straight line just going left to right. When we get like an equation like this, like y equals x plus 3, right? Now we get a line that has a little bit of a slant to it. When we get this, y equals x squared, it's like x squared minus 3, because you can see it's down a little bit. That's when we start to get this curve, this parabola. And now when we start seeing things like x cubed, x to the 4th, x to the 5th, right? These are all what's going on here. And you kind of see some ideas of what's happening. This x to the 4th, though, seeing how the center is shifted up, is going to be plus something. So I'm going to say like x to the 4th plus 6. I'm just guesstimating what these equations are. There's something like this. Just so you can kind of get a feel for what they should look like. Some patterns that you might observe here is, like this guy with 3 has a bump and then a bump. It has 2 bumps. One with a 4th degree has 1, 2, 3 bumps. 5th degree has 1, 2, 3, 4 bumps. So take the degree, take away 1, that's how many bumps it has. Also, something else you might observe is that the evens end up going in the same direction, while the odds end up going in opposite directions. So we can kind of see what their end behavior is just based on the degree. So we can talk about that. So let's ask ourselves then, what would happen if it was an even function, so it should end up in the same direction, and it's positive? Well, that means it's gonna do something like this. So that means its end behavior is going to be as x approaches infinity, f of x will also approach infinity. And as x approaches negative infinity, f of x will also approach, not negative infinity now, positive infinity. Just kind of look at this graph. As we go farther and farther to the right, it's going to keep going up. As we go farther and farther left, it's still going to keep going up. So that's what we mean by end behavior. So let's talk about if the function was odd and positive. So odd degree, but still positive leading coefficient. Well, we could sketch a little graph. It would probably look something like this. Right? So that means as x approaches infinity, f of x, which is the height, the y value of the function, is going to also approach positive infinity. But as x approaches negative infinity, f of x is going to approach negative infinity. Because you can see, as we go to the right, it keeps going up and up, but as we go to the left, it keeps going down and down. Okay, so we could kind of get some ideas of what's going on here. Let's talk about even and negative. Well, even and negative is going to look something like this. It's going to have some curve down, so now we can tell, okay, as x approaches infinity, f of x is going to approach negative infinity, because as we go to the right, the graph goes down and down and down. And then as x approaches negative infinity, meaning as we go to the left, f of x, the height, is going to also approach negative infinity. Alright, last one, odd and negative. This is just going to be the reverse of this guy, so that means it's going to start from the top, go down, so as x approaches infinity, that's a pretty ugly infinity sign, f of x approaches negative infinity, and as x approaches negative infinity, as we go to the left, f of x will actually approach positive infinity. Okay. There's some basic things that happen to our functions. You kind of want to have to just memorize these properties of like where it'll end up. If you can sketch a graph of it real quick based on these two things, help you quite a bit, especially when it comes to graphing. You can quickly at least see where it's going to end up, and helps you understand if you're graphing it right. So for this last one, I want you to describe the end behavior, determine whether it represents an odd degree or an even degree function, and state the number of real zeros. Okay, so I'm going to do the first one with you. So this is A, I. Describe the end behavior. Well, as x approaches, let's just look at it. As x approaches positive infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches negative infinity as well. Alright, so there we have our end behavior. What's the next one? They want to know, determine whether it represents an odd degree or an even degree function. We'll take a look. They're both ending in the same direction. We said earlier that's what even degrees do. So, even. And this one says state the number of real zeros. The number of real zeros is how many times it actually crosses the x-axis. Well, this looks like it's actually a fourth degree function. It has 4 zeros. Only 2 of them are real. The other 2 will probably end up being imaginary. So we're going to say this one has 2 real zeros because it crosses the x-axis twice. So 2. All right, I'm going to let you guys try these 2 on your own, and then I'll put the answers up in just a second. Okay, so I described what happens as x goes to the right here to positive infinity. It keeps going up and up to positive infinity for f of x. And as it goes left, it goes down to negative infinity. It's an odd degree because they're ending in opposite directions. And there's only 1 real zero because it only crosses it once. Here, as x goes to the right to positive infinity, f of x goes up to positive infinity as well. And as x goes to negative infinity to the left, f of x goes up to positive infinity. It's an even degree because they're both going up toward the same direction. And there's 0 real zeros because it never actually crosses the x-axis. All right, that's it for 7-1.